Okay, great. So, sorry, as I mentioned, I help run the Complex Systems Center at the University of Vermont, and we have looked up for a number of years to the Complex Systems Center here. Part of the reason why I'm here is to pick your brains about how things are going and hopefully build some bridges between our two groups. Speaking of the specific topic for the symposium, I want to talk about communication as it relates to robotics. As Louise mentioned, I'm a roboticist, and like many roboticists, I'm interested in trying to create useful and autonomous machines that can work alongside humans in the real world. But in order to do that, those machines are going to have to continuously learn and adapt to the changes that the real world throws at them. And they're going to need large numbers of human teachers to keep them on course. Personally, I don't believe that there is enough data out there in the universe for us to train autonomous machines in the lab, deploy them out into the world, and hope for the best. So part of the idea here is, how do we go about inviting large numbers of human teachers to collectively train and guide and correct autonomous machines as they work alongside people in the real world? How do we go about doing that? Well, an obvious choice would be to try and use natural language, which is, of course, the tool of choice for most of us when we collectively teach and train and guide each other. So I'm going to talk about my group's approach to trying to create autonomous machines that can understand natural language and respond appropriately. I'm going to talk particularly about some work from an undergraduate in my lab, David Matthews. So all of the errors I make this morning are mine, and obviously all the brilliant insights into language and autonomous machines are all David's. Okay, so we work on language in my lab, but I will start by saying we just dabble in language. I am not a linguist. That's part of the reason why I'm here today, to try and learn more about understanding of language and other disciplines. We also work in my lab on other aspects of cognition beyond language, like modeling of self and using self models to internally rehearse behaviors before trying them in reality. We work on damage recovery, so grappling not just with changes out there in the world, but changes to self. And as Luis mentioned, last week we published a paper on creating AI algorithms that automatically design robots made out of frog cells. These have been nicknamed the Xenobots. You might have seen them in the popular press last week. I am not going to talk more about Xenobots this morning, but for those that are interested in that project, I'm happy to talk about the Xenobots over the breaks. So we work on lots of different aspects of cognition, but our common approach to instantiating these different building blocks of intelligence in machines is the concept of embodiment. Embodiment is an old concept. It comes from psychology and philosophy. And generally speaking, the idea of embodiment is that the body is not an obstacle or an obstruction to intelligent action. It is a tool and it is an enabler. So if we look at biological systems, Mother Nature has sculpted the body plans of organisms over millennia, partly to help organisms push against the world and observe the sensory repercussions of their actions, and to use the data generated by that feedback loop through the body to the environment and back to the sense organs, to use that material as the foundation upon which to layer increasingly intelligent, adaptive, selectively advantageous behavior, and so forth. So if we take that idea of embodiment and port it into robotics and AI, we can ask the question, what is the appropriate body plan for a machine so that it can similarly push against the world, observe how the world pushes back, and use that feedback loop to build up increasingly useful behaviors, at least for humans. That's sort of the idea of embodiment. And as promised, I'm going to talk about our ideas, some recent ideas we published about how to use embodiment to help machines understand natural language. Before I talk about that, however, I want to situate our work in embodiment and others in the larger landscape of robotics and AI. So AI has been an ongoing enterprise since the 1950s. Collectively, we made sort of limited progress for 50 years until the 2000s. And thanks to the deep learning revolution and the big data revolutions, we made significant progress in just the last decade. And to talk about that progress, I wanted to use this sort of geometric metaphor. So you can imagine this one dimension of performance, and you can think about any point on this line as an agent. And I'll use the term agent as a catch-all term for a neural network, an autonomous car, a drone, a humanoid robot, a robot made out of frog cells, something that is able to push against the world and observe how the world pushes back. We can create training algorithms that produce a series of increasingly performant agents. So you can think of that training algorithm as a line segment embedded in this one dimension. And obviously, better training algorithms are able to push agents further to the right than others. So for some tasks, we now have training algorithms like the backpropagation of error, deep reinforcement learning, other training algorithms that are able to automatically train agents that are as good, if not better than humans at certain pattern recognition tasks. That's sort of the state of the art at the moment. But if we then introduce a second dimension, which is generality of our agents, we're not doing so well on this second dimension. So if you think now about these green arrows here, these represent different training algorithms. One of them trains an agent to play a good game of chess or Go. Another one trains an algorithm to recognize kittens in a YouTube video. But each of those training algorithms and the agents are specialists. The Go player is not able to recognize cats in videos, and the cat recognizer is not able to play a good game of Go. We're very good now at creating performant agents, but not specialized agents. So the overall open problem in AI at the moment is creating training algorithms that are represented by the red arrow here, which is training agents that get better and better at a gradually growing set of tasks. They're becoming more performant and more general. This is a much more difficult thing to do than just to train specialized agents. However, a lot of my colleagues in AI believe that with just enough data and some more math and bigger neural networks and enough compute, we'll eventually figure this out and gradually produce agents that become smarter and smarter and more general and general, and some believe will eventually approach human-level intelligence or superhuman intelligence. We'll see how that all plays out. But for most roboticists, they are also interested in a third dimension, which is this concept of embodiment. And embodiment means a lot of different things to different people. So for our purposes today, I want you to just think of embodiment as sort of the complexity of the body plan of the machine. So a naked neural network that's running inside a laptop has little to no embodiment. The simple Roomba has just a couple sensors and motors. It's still a useful machine, but it has a simpler or less embodiment than the Atlas humanoid robot that you see here. So I'm going to avoid defining embodiment. We'll just think about it as sort of this gradient towards more and more mechanical or morphological complexity. So in my group and some other groups, we're interested in training algorithms that push up and along the grand diagonal here. So we're trying to create training algorithms that not only produce agents that are better at something, but also become more general. And also, over the training algorithm, the body plan itself, the body plans of the agents are becoming more complex. So we're pushing to the right, up, and towards the back of the cube. And my colleagues and I who believe in this would contend that's a better path towards maybe not AGI, but at least flexible, useful, and embodied agents that can work well alongside humans here in the real world. Now, which of these two teams will win, we'll see, but I'm going to try and convince you about the utility of thinking about this approach. And I know there are a lot of biologists and natural scientists here, and of course this is how Mother Nature did things. She didn't create a body plan and then complexify nervous systems. There was a very complicated dance back and forth between evolutionary changes to body plan and nervous systems. Okay, so how does this relate to language? Well, I'm going to start with some observations from neuroscience. It's been known for a while now through brain imaging studies that there is an intimate relationship between action, the body, and language. For a lot of people, language implies sort of an abstract thing dissociated from the body, like mathematics or poetry or art. But if you put human subjects in a brain imaging device and you simply read to them, they listen to stories, you'll notice interesting things, like, for example, verbs that are related to the body, like talk, lick, grasp, pick, walk, and kick, will light up different parts of the brain, but they particularly light up parts of the motor strip, which is the part of the brain that would be underneath your earmuffs if you were wearing earmuffs. And particularly they light up parts of the motor homunculus in the motor strip. So, for example, if during the story the subject hears talk or lick, the mouth part of the motor homunculus will light up in a similar way to the human subject if they're actually talking or licking something, if they're actually using that part of their body, same part of the brain lights up. So this is a great oversimplification, but there's been a lot of studies that seem to support this. And even similar sounding words like lick, pick, and kick light up very different parts of the brain, and they light up different parts of the motor homunculus related to mouth, hand, and leg. So it's clear from neuroscience that there is this relationship between the body, action, and language. But as roboticists, what do we do with that information? How does that help guide us to helping machines understand language? So let's switch to machines now for a moment. We're going to see the world through a neural network or through a robot. If you start talking to a robot in any language, basically, this is what it hears. It hears a bunch of symbols that don't make any sense. You can try and supply definitions to the machine, but remember that the machine doesn't really understand any language. So it's almost like trying to learn hieroglyphics using a hieroglyph to hieroglyph dictionary. The machine sees some weird squiggle, has no idea what that squiggle means. It looks it up on the internet, and that symbol is defined by a whole bunch of other symbols, which it also doesn't understand. So it takes the next symbol, looks that one up, and gets caught in this infinite loop where it's not able to ground out the meaning of words in any ways. This is known as the symbol grounding problem, which again comes from philosophy. How do you get machines started on understanding language? It's a notoriously difficult problem. So one approach to cracking the symbol grounding problem in robotics is to use this idea of embodiment. So now we're going to try and bring in the body as a way to break this deadlock. And this sort of cartoon is a way to try and illustrate this process. Imagine we have a robot that understands no language whatsoever, but it does have sensors, and this robot just goes about its normal, goes about doing something maybe at random. And as it's moving over time, it's receiving sensory information. And it notices, this hypothetical robot notices that whenever the pressure on the soles of its feet goes to 0, as reported by its sensors, suddenly out in the world it hears 4 symbols, JUMP. Whenever this change in its sensory signature happens, it hears that. There's a temporal correlation between this sensor motor experience and these symbols that are coming from the outside, which you can imagine are coming from a human trainer who's watching the robot and is speaking whenever the human teacher sees some action that it wants to teach the robot. So the robot might be able to start to ground these abstract symbols, JUMP, in its own sensor motor experiences. If you were to ask this robot what JUMP means, it doesn't know any other words, so it can't answer you in English, but what it can do is look at you and jump. It can show you that it knows what JUMP means, which is maybe a start. The idea then is if we can ground motoric words like jump, pick, grasp, move, and so on, we might be able to turn this into a recursive algorithm where instead of grounding motoric words like jump directly in sensor motor experience, we can ground slightly more abstract concepts like movement in the symbols we just grounded. So, for example, this hypothetical robot may notice that JUMP only occurs when all of its pressure sensors go to 0, but there's another word, MOVEMENT, which it hears more often for a broader range of sensory experiences. Not all of its sensory experiences. It can sit still and it doesn't hear movement. So it can start to gradually, recursively ground these words, and it's a fun exercise to think how far you can get with this. One of my students argued that democracy would never be something that could be grounded in this way. And I pointed out to the student, if you ever played tug of war, you know physically what the feeling of democracy is like. Now, whether that would work for a machine, who knows? At the moment, this is sort of all theory. So in the experiment I'm going to show you now, we tried to actually enact this theory. Could we actually train a machine to ground symbols in physical action? So I'm going to show a few slides here which are somewhat technical. If you zone out during these slides, that's perfectly fine. But if you've ever wondered how your smartphone does autocomplete for words in your phone, this is kind of how it does it. So we're going to start with language first and then get to robots. So Google a few years ago, scraped 100 billion phrases off the internet. Here's one example phrase: the cat sat on floor. And they then tried to train a neural network where if you gave the neural network the first two words and the last two words, the cat and on floor, it would be able to predict successfully the missing middle word, which in this case is sat. It's easy to train a neural network to do this for one phrase and 10 phrases, but it takes the power of Google to be able to do this for 100 billion phrases. And it almost seems like magic, but once they did that, it turns out that now if you type something in on your smartphone and you have one of these trained neural networks or a version of it running on your phone or in the cloud, it can do this for phrases it's never seen before. Okay, so how does it do this? As I mentioned, we have a neural network and we have two parallel input layers in this cartoon here. And the way this works is we take our 5-word phrase and we take the word just before sat, which is cat, and the word just after sat, which is on, and we use a one-hot encoding, which means in the input layer we have zeros for all other words and we just light up the one neuron that corresponds to cat, and we light up the one neuron that corresponds to the word on, and we turn all the other possible words off. We then propagate using math those two vectors, those two binary vectors, through to the hidden layer. And at the hidden layer, you get a smaller vector, which is a whole bunch of real values, floating point numbers. And then those hidden layer values propagate out to the output layer. And we force the values arriving at the output layer to be either 0 or 1. And we allow only one of those numbers to be 1, and all the others have to be 0. And most of the time, the computer will get it wrong. It will turn on the word for, I don't know what, something other than sat. So we penalize that neural network, change the internal synaptic connections, do this again, and we keep going until it lights up the neuron associated with the word sat. And then we go on to the next phrase and the next phrase. It's a very big trial and error process. And if you do this, it's amazing what's possible. At the end, you get two matrices, uppercase W and uppercase W prime. W prime is a matrix that will take some internal representation of the phrase, which is unintelligible to most humans. You push that internal representation through the matrix W prime, and it will light up one of these words, which is usually the correct word. Now that Google has trained this massive neural network on 100 billion phrases, we can take W prime and invert it. And what I mean by that is now we can turn things around. We can take a new word, like sat or some other word, and push it through the right-hand side back through W prime, and we'll get this hidden layer vector, a vector of numbers, which is the neural network's representation of that word. And I know I'm straying into words like representation and meaning and so on. For our purposes, representation is just a vector. And that's why the early version of this was known as word2vec. We take a word, a natural language, an English word, we push it through this trained neural network, and it'll give us back a vector. Google has now figured out lots of uses for this word2vec process. In work we did last year, we adapted this for robotics in the following way. We're going to have a robot. That robot has sensors and motors, represented by S and M here. The robot has an internal neural network, which controls its actions. And what the neural network is going to do inside the robot is transform incoming sensory signals into outgoing motor commands, not unlike nervous tissue, which transforms sense organ signals into muscle activations. We're going to add an additional neuron to this neural network, which is the auditory neuron, A here. And we're going to take a word that we want to train our robot to obey, which in this case is forward. We're going to take forward and push it through this word2vec neural network that Google produced. And that word2vec is going to give us back a vector, which is just a collection of numbers. Means nothing to us, means nothing to the robot yet. But we're going to push that vector of numbers through the auditory neuron before we allow the robot to move. So you can think of this as us holding the robot still and whispering in its ear, and it's receiving these numbers, and these numbers are flowing from the auditory neuron into the hidden layer, the guts of the neural network, and they're setting the initial values of those hidden neurons. So the robot is we're priming the pump of the robot. Once we do that, once we push the entire vector through the neural network, we let the robot go. And in this case, this is what our robot does. As you can see, this is a simulated robot, not a physical robot. So what happened here? Well, just to back up for a moment, remember that we said forward to the robot. It set the hidden neurons. And the moment that we let the robot loose in its virtual environment, it started to also get input from the sensory signals. So what's happening at the hidden layer, the internals of the robot's brain, is it's mixing the numbers from word2vec, and it's mixing its own sensory experience. And those two flows of information come in, they send signals to the motors, and the robot does something. So far, so good? Any questions? Okay. So in this case, the robot actually moves forward. And this is because you're watching not a random robot, but a robot that's been trained. So I'm kind of jumping ahead a little bit. But imagine this robot just did any action. It doesn't really matter. Well, we told the robot forward, and it acted. We then pull the robot back to the origin, wipe its brain clean, and now we whisper backward to the robot. So it hears, this robot with the same brain hears a different set of numbers corresponding to backward. So now the pump is primed differently, and it starts moving, and it moves differently because it heard something else. And in this case, it kind of moves backward. Same robot, same brain. We've now evaluated it twice with two different words, and we continue this process. So we now, we whisper stop in its ear, and it does this. We whisper cease in its ear, and it does this. We whisper suspend, and it does this. And now, this is during the training process. So I'm sort of skipping ahead a little bit, and I'll back up in a moment. So the robots have actually been trained for a while, and as you've seen, this robot is pretty good. It's kind of obeying the 5 things we asked it to do. The important step for us here is after training is done, after we've done our best to teach this robot, we're going to put it back in the world, and we're going to issue a word that it's never heard before. Let me just jump ahead here, which is the word halt. And this is what the robot does when it hears the word halt. So we are one of 2 groups this past year that reported robots that are able to respond appropriately to words they've never heard before. And the reason why this is possible is because we're borrowing this word2vec, the power of word2vec. Okay, so as I mentioned, you're kind of seeing the end of the experiment after training. So let me back up and talk about how we actually trained this robot. We started by taking one robot with a random brain. We then issued the word forward. We watched what the robot did, and we computed the fitness F of the robot. And the fitness is simply how far to your right the robot traveled. How far along the x-axis did it move? The further it moves forward, the higher its fitness. We then issued the command backward, and we measured how far it moved to the left. When we issued the commands stop, cease, and suspend, it got more fitness when D was lower. So D is distance, right? So basically it's penalized for any movement whatsoever. So we're basically telling the robot now what the meaning of these words are. When you hear F-O-R-W-A-R-D, you should move to the right. Now, how you figure out how to do that, that's up to you. So we have to pair these words with our understanding of what they mean, which is a bit of a limitation, but we'll come back to that. So we take each robot and we compute F 5 times using these formulas. And we then wrap this robot in an evolutionary algorithm. An evolutionary algorithm, as the name implies, is a gross simplification of natural evolution. What we do is we create actually a population of these random brains. We take each random brain, drop it into the robot 5 times, and compute the fitness of that brain. Drop the next brain into the robot 5 times, compute the overall fitness, and compute overall fitness for every brain in the population. Brains that get higher fitness, meaning they cause the robot to obey those 5 commands better, are retained. Those that did a worse job are deleted. And the evolutionary algorithm then makes randomly modified copies of the surviving brains. As you can imagine, most of those mutated brains do much worse when they're put back into the robot. It's random mutation. But a very few of those mutated brains actually cause the robot to obey, on average, slightly better than previous brains. And we repeat this process on a supercomputer for days or weeks or months. And at the end, we get the brain that you just saw in action. It's able to generally obey these 5 commands. Any questions? Yes, Charlie.
Then we give it halt. Is it because the vec for halt is somehow close to the vec for stop, cease, and suspend?
Exactly, right? So why does it obey halt even though it's never heard that command before?
But how does that translation know?
How does that translation know? So we're going to just dip our toe into word2vec. It's a fascinating subject in and of itself. One of the magic things about the word embeddings, which are the vectors associated with the words produced by word2vec, is that they seem to retain the semantic structure you would expect them to have. So here's just an example of this. Here's the 6 words that we were using with our robot. And in each pair of words, we're reporting the cosine similarity between the 2 vectors associated with those 2 words, which is just obviously how close those vectors are to one another. And as you would expect, as an English speaker, halt, stop, suspend, and cease have higher cosine similarity to one another than, for example, backward and halt do, right? So our intuitions about the meaning of English words seems to be preserved more or less by word2vec. So in retrospect, it seems kind of obvious now that the robot would behave similarly when it hears halt because it's heard those words before. But it turns out in this experiment, it's not as simple as that, and I'm going to spend some time sort of unpacking that. But on the surface, it kind of makes sense. We have word embeddings that preserve semantic structure, but we're going to try and push those embeddings through robots. So they're going to translate those word embeddings into sensory signals and actions. If we take that next step now from embeddings to action, are the robots able to preserve that semantic structure in behavioral structure? Do they act similarly when they hear semantically similar words? And it turns out in this case, yes. One of the reasons for this is you'll also notice that The robot heard more stop commands than go commands, right? 3 stop commands and 2 start commands. So it could be that the evolutionary algorithm just got lazy and it'll just cause the robot to stop unless it hears forward or backward. So it's kind of there's a bit of a flaw in this approach. So we redid the experiment and balanced the commands that we sent to the robot. So we reran the evolutionary algorithm and evaluated every robot brain 6 times. It heard forward, and forward. So word2vec handles misspellings as well. We fed it backward and backwards, and stop and suspend. So at the end of the evolutionary algorithm, the evolved brains had equal experience with forward, backward, and stop commands. We issued the command cease, and again, it tended to stop when it heard this unfamiliar word cease. So let me walk you through some data to sort of illustrate, again, why this is not as trivial as it might seem on first reading. When we trained the robot on these, we trained the brains on these 6 commands. When we issued the move commands, the 4 move commands, on average, the robot would move about, whatever that is, 4 or 5 or 6 body lengths forward. It was definitely moving. When we issued the 2 stop commands, stop and suspend, on average, the evolved brains would cause the robot to stay still. And when we issued cease, after training, after evolution, indeed, on average, the robots would tend to also not move. And we wanted to know whether that was, again, because of the semantic structure in word2vec. So we took the 7 vectors associated with these 7 commands, and we permuted all the values in the vectors. So we basically disrupted whatever structure there is in these vectors, if there is any, from the point of view of the robot. When we redid the experiment, when we re-evolved the brains on these permuted 6 vectors, the robot still learned to go forward when asked to and backward when asked to. It also learned to stop when it was told to stop and suspend, even though those vectors were garbled. And now when it heard the garbled cease, it had no idea what to do. So clearly, the evolutionary algorithm is exploiting the semantic structure in word2vec embeddings and preserving them in the sensor motor trajectories of the machines. Yeah, makes sense? Okay. So far so good. So people have been trying to teach robots language for a long time, and now it suddenly seems this is super easy because of word2vec, but of course in science that's never the case. So as I just showed you, this is one possible answer to the question of how to train a robot to ground language in the soil of its own sensor motor experience. But if we think carefully about embodiment, we can ask a different question, which is, what robot? So this robot did it, at least for these very simple commands. But if we issued that robot 20 or 30 or 100 or 1,000 or 10,000 words, would it still be able to do it? Imagine a different hypothetical robot that when issued the command JUMP, this is what the robot experiences. This robot is going to have a very hard time grounding this symbol in its sensor motor experience compared to this one. So we can now come back to this concept of embodiment and ask the question, what is the right embodiment for a machine to be able to preserve and translate semantic structure into behavioral structure? So we tackled that in this paper. We used that simple 4-legged quadruped that I showed you. David Matthews created 2 other robots, the ball bot that you see here. And the ball bot has inside it, which you can't see, a pendulum. And it can move that pendulum, which causes the ball to roll in different directions. And it turns out the ball can more or less obey. But if you look at the blue bars associated with the ball bot here, those blue bars are significantly taller than the blue bar for the quadruped. So it turns out that the ball bot has a much harder time obeying the unheard 7th command, cease, than the quadruped. So the quadruped is better at grounding language than the ball bot is. And there's this simple scissor bot that David created, which also has problems with obeying. It obeys very well, but doesn't move at all. It also has some problems. So we looked at 3 different body plans, and for those 3 different body plans, for some, evolution is able to ground language in that body plan better than others. Okay. Why is that so important to us? Well, I'm going to try and illustrate this with a little cartoon. So in this first experiment, we're using very simple language. But how is this going to scale up? Let's take our 3 sets of synonyms that we have here, and I've embedded them in a 2-dimensional space. And imagine that our robot has just 2 sensors. When it hears either forward or forward, those are similar vectors, thanks to word2vec, which means the robot is going to start moving similarly when it starts moving. It's heard almost the same thing, which has primed its pump in more or less the same way, and it's going to jump out of the gate in more or less the same way. The same robot, if it hears backward and backwards, those 2 words are different from forward and forwards, so we're priming the pump differently, which means whatever this robot does, it's probably going to do something different, which is okay. Same with stop and suspend. Now, if we think about the quadruped for a moment, as the robot starts moving, the sensor values are going to change, which are represented by the black arrows here. Just because the robot started in a similar place, it had the similar sensation because it just heard the same word and started moving, there is nothing to guarantee that as the robot starts moving in these 2 different situations, that it will continue moving in the same way. So if we look at just the 2 forward words here, the robot starts moving in the same way, but there's nothing to guarantee that it won't start turning and doing something completely different. And the reason why is that most machines and organisms are nonlinear systems, meaning that as they interact with the world, that feedback loop is nonlinear. And even if the start of that feedback loop is very similar, even if we start with 2 very similar initial conditions, the robot's behavior can quickly diverge. So it's not trivial that the robot actually did the correct thing when it heard cease, because there was every reason that the quadruped could actually do completely different things due to the fact that it has a nonlinear relationship with the world. So the nonlinearity makes it harder to preserve semantic structure into the behavioral structure of machines. If that's true, then why don't we just get rid of the nonlinearity and make simpler machines, because we can design these machines however we want. So why don't we make simpler machines that tend to preserve initial conditions? Fine, we could do that, but this ball bot, although it may be able to go forward, backwards, and stop, it's not going to be able to obey the command, pick up the object or jump over the obstacle. It's it's linear, but also means it's simple, which means it's just not going to be able to ground other language because it just doesn't have hands and arms and legs and so on. So what that tells us is there's probably a sweet spot between overly complex robots with nonlinear behavior, which in theory could obey all the commands, but it's going to be hard to get them to do so because of this nonlinear property. And we don't want overly simple robots because although they'll preserve semantic structure easier, they won't be able to obey. So how do we find that middle ground? How do we find the right body plan for the commands we want the robots to ground? That brings us back to this concept of embodiment. How do we create training algorithms that not only train the brain of a robot to obey language, but is also altering the body plan as the training algorithm goes? So in just a cartoon example of this, imagine we started with a morphologically simple robot that had no arms and hands, and we just trained it to move and stop moving. Once it mastered that small set of commands, we might allow evolution to start to tinker with the body plan and add the rudiments of appendages and arms and fingers and so on, but just enough that the robot could start to obey, pick up, grasp, touch, point at, and so on. That's the idea. We haven't got there yet. but we have been sort of building the machinery to try and do this. And the machinery is actually online. You can go play with this on your own. There's the URL, twitch.tv/twitchplaysrobotics. If you've never visited Twitch TV, it's quite a ride. It is one of the 10 biggest websites on the planet. It is massive. Most people use it to watch other people play video games and comment on their gameplay in real time. It's an amazing cultural artifact in and of itself. There's thousands and thousands of channels inside of Twitch TV. We launched our own channel called Twitch Plays Robotics. If you go to the TPR channel, instead of watching somebody play video games, you watch a live stream of our evolving robots. In that live stream, you're shown pairs of robots, one after the other. And you'll notice that for each pair, they have been issued a command. In this case, the pair heard nodding. In this case, the pair hears movement. And as you now know, what the robots are actually hearing is the word embeddings associated with these commands. What's not shown here is the chat window, the live chat that goes along with Twitch Plays Robotics. So as humans are watching this, they can type into chat G if they think green is better than purple at ripping, or P if they think purple is better than green at ripping, and so on and so forth. So we're getting, again, this idea of human teachers, which are trying to help robots ground natural language in their actions. I grabbed this video this morning. So this morning, not a lot was going on. The body plans are kind of non-intuitive, but kind of an interesting thing to watch. As this process is running, and we've been running Twitch Plays Robotics for about 1.5 years now, the evolutionary algorithm is making slight changes to the body plans and the neural network controllers of these robots, unbeknownst to the human players. And the idea is that if evolution hits on body plans which admit the grounding of language, it'll be easier for the humans to help with that process than otherwise. We're still looking at the data. It's hard to say at the moment whether that's actually working, but you can go try this out on your own. Another twist to TPR is that it's not us that issue the commands. The commands are actually issued by the crowd itself. So we tell the crowd to think of these things as sort of simple pets or certain animals. In theory, they are capable of learning to obey a few commands, but probably not many. And the game for you, the human participant, is to figure out with your friends what those words are. I gave you the example of jump before. It turns out that the crowd issued the command jump, and enough people supplied reinforcement under the command jump that some of these robots actually, when you type in JUMP, they will jump. They, quote unquote, understand what jump means. We have a long list of commands issued by the crowd. One person typed in the command, be interesting. It was kind of interesting. Somebody else said, be yourself. That one was interesting. Solve Fermat's last theorem. That was another one. Every swear word you can possibly imagine in any language has also been issued to these robots. It's quite an interesting data set. Okay, I will just start to finish up here. As a good roboticist, we did everything not just in virtuality, but also in reality. So David Matthews, I mentioned, the undergraduate working on this project, also ran this algorithm, this evolutionary algorithm, on a physical robot that he and some of his student colleagues made for a class project. Here's the robot hearing forward. Doesn't do a very good job, or maybe my video's skipping. Let's try this again. Here's forward, not bad. Here's backwards, same robot, same brain. When it hears backwards, it disobeys, doesn't understand backwards yet. Here's halt, not bad. Cease, and suspend. During training, so these are things words it's heard many, many times. And then finally, a word it's never heard before. So again, not great, but this is the first physical machine that is able to more or less obey a natural language command it's never heard before. So again, this is just some preliminary work from this past year. We dabble in language, so I'm interested today in learning more about language and getting input from the real experts on language on where we might take this next. There's the citation to the paper if you're interested in the technical details. All of the code to replicate this experiment is up on GitHub. I also run an online course, and we're in week 2 now of that online course. It's available at Reddit. It's called Ludo Bots. Ludo is Latin for play. In Ludo Bots, you complete a series of 10 programming projects where you gradually build up a simulated robot, a simulated environment, and then you gradually wrap an evolutionary algorithm around this virtual environment. And at the end of these 10 programming projects, you can then try out an evolutionary robotics experiment of your own. There's the link for Twitch Plays Robotics. Thanks to NSF and DARPA for funding parts of this work, and my very camera-shy colleague David Matthews, who did all the real work here. I'll stop there and take questions. Thanks very much. Yes.
This is really exciting. Thank you so much for sharing that.
Sure.
I guess a high level. I have a lot of questions, but I'll
Sure.
ask a high level question. The co-evolution of the understanding and body plan.
Yes.
Was interesting and exciting, but it seems to be a little bit at odds with at least what the human species experience was, right? So it wasn't the case. Oh, thanks. Sorry. I'm asking about the co-evolution of bodies and language. And so for humans, at least, it's like, it doesn't seem likely that we were reorganizing our body plan at the same time we were figuring out words.
Okay.
It seems the body plan was fixed. So I just want to get your thoughts on why you see that co-evolution as particularly insightful.
Yeah, so again, I'm not an expert on language, particularly human language. So I mentioned this as language throughout this talk. I guess I would consider this more communication,
Yeah,
right? So you know, this could even be gestures. The vectors themselves are kind of immaterial, right? It's what is the simplest signal that a human can provide to these evolving machines, where evolution responds with body plans that ground it. So, you know, abstract language like jump and go pick up the block, it's a little bit of a red herring, right? It's really just communication and simple signals. But the signals are rich enough that there is semantic structure in there, right? Some signals are more similar to others than others.
Thank you.
Sure.
This is so cool. So I was wondering about so the use of natural language,
Yep.
right? So I would assume that our words arise out of our particular body plan, right? So I wonder if you had thought about this for our sphere boys, right? Like,
Right.
would it be possible for them to go around, maybe develop kind of their own words or kind of symbols for the particular things that they do, and then translate that back in so that there could be like a language amongst the spheres that we don't understand?
Yeah, that's a great question. So there's some really amazing early work from the 1990s by Luke Steels, a roboticist and also a linguist, who really explored this issue of if robots are different from humans, will they create language which is different from ours? So this is related to that work, but also different because in Steels' work, the robots were actually creating their own vocabulary and even grammar and all that. Here, they are not allowed to do so, right? They have to use human language, and not only that, they have to use the semantic structure latent in the word embeddings, but they alter that structure the minute they start moving, right? So again, what does it mean if you say, pick up an object between your thumb and forefinger? Right? A robot that doesn't have that body plan, what is that going to mean to the robot? It's not immediately clear that it's going to be ungroundable because it doesn't hear thumb and forefinger. It hears something that's related to hand or manipulator or gripper or Velcro or whatever the robot has. So I think it'll be really interesting to explore what body plans not only ground language, but which body plans ground it as similarly as humans ground it. That would be a fascinating thing to tackle next. Yes?
So, years past, there
Oh.
was developments. In years past, there was some developments in robotically created languages.
Yep.
One of the early ones was the IEF, what was it, the something engineering facility.
Okay.
I recall, produced at Texas Instruments, I believe, like a long time ago.
Oh,
1980s
okay.
or something.
Not familiar. Okay.
And I wondered if you'd compare that to anything that's been developed since, in terms of any leaps forward in language creation. You could, from the IEF,
Yep.
at that time, create COBOL and C programs by simply using some very simple English commands
I see. I
that
see.
were very similar to, say, SQL.
Oh, that's interesting.
And that platform was actually used for the development of what was once known as the Sabre system, developed by American Airlines in their technology division.
Okay.
And that's a long time ago. So I wondered if you're familiar with any developments in this kind of secondary language creation.
So I think, if I understand you, this is a translation from natural language into code.
Yes.
Okay. So here we're interested in natural language to action, right? So there's no code. I mean, there's code in terms of the neural network. So I think it would be interesting to look at these different kinds of translation systems. And Google and others are obviously doing lots of interesting work and using word2vec to facilitate lots of different kinds of translation, right? So from natural language to technical language, I think there's a lot of interesting developments there. We haven't personally looked at some of those other systems. We're focused specifically on language to action, physical action.
Some people look at like foreign language translation,
Yep.
done by Microsoft years ago, to be like a similar
Yeah. So
kind of endeavor and very advanced at that time.
yeah, so we have actually a significant Spanish-speaking population on Twitch Plays Robotics, which is interesting because, at least in theory, the Spanish words, if you push them through something related to word2vec, the Spanish word for jump and the English word to jump actually have high cosine similarity. So it should be relatively straightforward to train these robots to be bilingual. When they hear the German or the English or the Spanish motoric word, they're getting similar vectors, so they should even be biased before training to do similar things. Whether that's existing in this data set, we don't know yet. I think there's a question over there.
This is really fascinating. I noticed on the Twitch Plays Robotics interface that you have the family tree information
Yes.
from the evolutionary algorithm. And so I'm curious whether you've sort of analyzed the statistics of the evolution of the various neural network architectures and so on, to see if, for example, some of the signatures that you might see in biological evolution, like the emergence of a kind of keystone innovation or something like this that opens up greatly enhanced capacities in translating the word vectors into motoric action or something like that shows up.
Yeah, that's a great question. So we definitely have the complete fossil record of all of these robots. We have not found evidence of any actual evolution going on yet. And the reason why is because we allow the users to propose commands. So there's 10,000 commands, and we'll get one robot that kind of obeys one command and maybe a second one, and none of the rest. And then it's immediately evolved out of the population because there's some other robot that obeys another 2 commands. It's too unconstrained at the moment. So one of my grad students who's working on this is working with the interface to constrain it. So can we help users see that evolution is starting to make progress on just this one command? So focus your effort, human participants, on this command and these neighboring commands. So word2vec, one of the things it will do is if you give it a word, it'll give you back a cloud of semantically similar synonyms. So we might be able to help clarify a pathway for humans to provide reinforcement, which is a sufficiently strong signal to actually start to see evolutions of body plans that ground language, but we're not there yet.
Thanks. This might be a word2vec question.
Sure.
But so I was curious just because you had forward and backward, and there's similarity there that's in the form, and not really probably in the meaning when it comes to how it's being used. Or that's actually, so the general broader question is, when there's redundant information, that word part is not really giving it any additional information. It's redundant across the two things. What happens here, and are those like forward and backward, do they cluster closer together than we would expect?
Yeah, that's a good question. We haven't looked at the sensor data itself. You could see if it basically just converges on exactly the same action. So I don't know if those two initial conditions, forward and forward, if evolution tends to just say, listen, they're the same thing and it converges, or does it preserve the slight difference which does exist in the embeddings themselves? Whether there's a pattern there or not, I don't know.
I meant actually forward versus backward.
Oh, okay.
Right, the W-A-R.
I see.
Yeah, but actually that's also a good question.
So word2vec doesn't drill down to the character level, to the letter level. So word2vec does not know that W-A-R-D is redundant in these two words. According to word2vec, they're different words, but they're similar words. Yeah.
Thanks, Josh. We've got a coffee break that we can continue the conversation.
Sure.
Let's
Great.
thanks, Josh.
Thanks very much.